Hello learners, welcome to session 3 of week 3 in the course Introduction to Abstract Algebra. So in week 3 we are looking at algebra of numbers. In session 3, in particular this tutorial, we are looking at modular arithmetic. One of the arithmetic structures that are frequently used in number theory in abstract algebra is the modular arithmetic. So modular arithmetic is also called clockwise or clock arithmetic because the rules of addition resemble the rules for addition on a clock. You remember when you were doing modulo in secondary school, you're using a clock. The teachers use clock to do demonstrations. So in this session, we learn the properties of modular arithmetic. We shall also use the modular arithmetic to define various aspects of congruence in this session. Okay, so let's begin. By the end of this session, you should be able to give examples of the use of modular arithmetic in algebra. You should also be able to determine inverse of modulo explain the relevance of modular arithmetic in abstract algebra. You should also be able to use modular arithmetic in proofs in algebra. Definition: modular arithmetic. So for a positive integer m and integers a and b, we say that a is congruent to b modulo m if and only if the m divides the difference between a and b, and we denote this by a is congruent to b modulo m. So if you want to be more precisely, you can also introduce brackets to separate the modulo from the a and b. So a is congruent to b modulo m implies that m divides the difference between a and b. Okay. So, otherwise, A is not congruent to B modulo M. A is not congruent to B modulo M. In the above notation, M is called the modulus, and we consider the integers modulo M. So, make sure you take the definition, very, very important. Okay, let's look at this theorem. If A is congruent to B modulo M, and then C is also congruent to D modulo M, then we say that A plus C is equals to B plus D mod M, and otherwise we also multiply A C equals to B D mod M, and they are true. So if you call this one equation 1, let's say equation 1, okay, here, and then we call this equation 2. So equation 1 plus equation 2, we get this one. And equation 1 times equation 2, we also get this one. And they are all true. Let's look at the proof. So if A is congruent to B mod M and C is congruent to B mod D mod M, then there is this integers K and L such that A equals to B plus K M. Likewise, so we can call that equation 1 and call this equation 2. C equals to D plus L M. Don't forget about your divisor theorem. Okay, so if equation 1 here and equation 2 are true, then what can we say? Then we can say that when we add equation 1 plus equation 2 gets A plus C, and that is the same as B plus D, and then K plus D, you factor M out, and that is true. Therefore, A plus C will equals to B plus D mod M, and hence the first one is proof. Secondly, when you multiply equation 1 by equation 2, we can have this equation. I'm trying to add this equation 1 star and this equation 2 star. Okay, so if you multiply equation 1 star by equation 2 star, so you get AC, that is A times C. AC equals BD plus DKM plus this expression here, So you can simplify this expression and then we get mode M here, PD mode M, hence we also proof for that. So this proof is just simple, very interesting. Simple and also interesting. So find more useful facts about modular arithmetic in your course outline. Let's look at this example. Solve the following equations in modular arithmetic in the domain of natural numbers. So the first one is that is 3x plus 2 is congruent to 2 mod 4. So in solving this one, you can say 3x plus 2 equals to 2, making x a subject, get x equals to 0. So we are solving for the unknown quantity x. The same happened here, 2x minus 3 equals to 1. So when you do that calculation, you get x equals to 2, you do that one here. And this one D here, x squared equals to 0, so you get x equals to 0, x equals to 0 twice. So this one is repeated. Okay. But here you get x equals to plus or minus 1. Remember, we are dealing with modulo, so we are interested in the positive remainder. Because when you talk about modulo, the remainder should be in your head about remainder theorem. So the answer is the positive 1. Great. And even when it's negative, you put negative there, you get 1. But we are dealing with modulo. Inverse of a modulo. If ax is congruent to 1 mod m, then we say that x is the inverse of a mod m, denoted by a inverse, and it is unique mod m. That is how, right? It's inverse and it's unique mod m. So the inverse of a mod m exists and is unique if and only if a is relatively prime to m. So don't forget about your prime numbers we discussed. Okay, let's look at the proof in the next section. So this proof is just simple as I've explained. If ax equals to 1 mod m, then we can say ax equals to 1 plus km. Don't forget about your prime numbers. Okay, for some k, and then when we try to group like that, bringing km to the other side, we get this one to be less equation 1. So the positive integers a and b are relatively prime if there exist integers x and y such that ax plus by equals to 1. You remember, and that is integers, prime numbers we discussed in the previous session. So going through this proof is so simple. In order to shorten this video, I skip this proof for you. Go through the rest, it is in your course outline material, and it's so simple. Let's look at the Fermat's-Little theorem. If P is prime and P does not divide A, then A is congruent to 1 mod P. So we need this equation, this theorem, very necessary. Let me call it star. This is star. If P is prime and P does not divide A, then according to the Fermat's-Little theorem, we have A exponent B minus 1 is congruent to 1 mod P. Great. Okay, so we look at example 15. If P is a prime and n is an integer, now we prove that P divides 4n squared plus 1. So show that P is congruent to 1 mod 4. We prove this one by contradiction. So let's suppose that P is equal to 4k plus 3 for some k, and then let y equals to 2n. So by the Fermat's-Little theorem, y raised to the power p, that is theorem, is congruent to 1 mod p. And since p does not divide n, it's prime, but y squared plus 1 equals 0. And when you put 2n into 4n squared plus 1, what do you get? You get the same thing. So y squared plus 1 equals 0. And this implies that by the Fermat's-Little theorem, y with the power 4k plus 2, that is, you put 4k plus 3 into where you see p, So that will be like, it looks like this. Y raised to the power p, that is, and now p is 4k plus 3 minus 1, and this will be equals to y raised to the power 4k plus 2, which is here. Okay, and when you factor the 2 out, you get this one. And you agree with me that this is equivalent or is congruent to -1 mod p. So there's contradiction here, therefore p is congruent to 1 mod 4. P is congruent to 1 mod 4. So simple. Congruent definitions. Let's be a member of natural number or natural numbers. The congruent relation modulo m is an equivalence relation that satisfies the following properties for all any a, b, c being congruent to the integer z. So a is congruent to a mod m, and that is reflexive. And I remember you remember this, if you've done that already. Once a is congruent to a, that's every number related to itself relation. Then we say that a is congruent to a mod m. Then symmetric or symmetry. If a is congruent to b mod m, then automatically b is also congruent to a mod m. And we look at the last one. If a is congruent to b mod m and b is congruent to c mod m, then a is congruent to c mod m. Transitivity. Okay, and look out for these proofs. They are very necessary and very, very interesting as far as this course is concerned. Let's look at residue classes. Let's M be a member of N. The equivalent classes defined by a congruent relation with M are called the residue classes modulo M. For any integer a be a member of Z, the equivalent class of A denotes that equivalent class to which A belongs. That is, equivalent class of A is equals to N is a member of Z, and N is equivalent to A mod M. Then we say we have what we call residue classes. Now, complete residue system. A set of integers 1, R1 to Rm is called a complete residue system modulo M if it contains exactly one integer from each equivalent class modulo M. Okay, so read equivalent class of and look for out the proofs. You read more on the equivalent classes, and then you also look out for the proof for this. They are very, very interesting. In this course, you do more proofs. The more you do the proofs, the more you understand better. Least non-negative residue. If we let n be a member of natural numbers n. Now, for any integer n, the least non-negative residue of modulo m is a unique integer r such that r is congruent to r mod m for this given interval. Okay, so that is r is the remainder upon division of n by the division algorithm. So don't forget about that.